Thank you very much. Good afternoon, everyone. So definitely the previous section on stablecoin actually draw a lot of attention. This is really great. And this time is a little bit special. Is that we are actually having this post-quantum blockchain day while having a little bit technical section arranging. And anyway, this is our first event, and in the future we would like to have this cryptographer section happening every single time, so that we will be able to basically want to share two things. That's basically my agenda. The first one is to hear from the cryptographers about the hot topics that they are working on, or in the cryptography field, what kind of hot topics they are, and how they are related to blockchain. So I think investors may also be very interested in these topics. Just like in the past when we talk about zero knowledge proof, but actually for cryptographers, we have been working on that for decades. And it's actually very happy to see zero knowledge proof systems has been used quite widely in the blockchain industry. So today I would like to hear from the professors here about the latest hot topics in cryptography and why they are very useful, they are impactful for blockchain. Another purpose I would also like to achieve today is to find out from the cryptographers about why it's so complicated and why it's so difficult to build such a, not just a post-quantum blockchain system, but also having different layers of privacy. What kind of tools you guys use, and how we will be able to achieve that. Yeah, by the way, we work together. So to start with, maybe we can introduce ourselves a little bit. What I would like to do is to start with Professor Yang. He's the most junior one among three of us. And then I'm going to introduce myself, and also and then finally Professor Wang is going to introduce himself. What I would like to do is to hear from each of you about what's your background, what hot topics you are working on, and what's your focus. Yeah, Professor Yang, please.
Okay, thank you, Duncan, for the introduction and for having me. So I'm Guomin from SMU. Actually, I did all my degrees in Hong Kong. I studied crypto research since 2004, actually under Duncan. Duncan actually was my supervisor. So we have been working together for 20 years, right? So
together, 2 decades, right?
Yeah, 2 decades. Actually, I also knew Prof. Wang when I was a PhD student in Hong Kong. So yeah, so yeah, it's I'm always very pleased to come back Hong Kong, because I stayed here for near 10 years, right? So, and then to introduce my research. Actually, my background is crypto. So and then my current focus actually is more on the privacy enhancing technologies, including the applications of these technologies in blockchain. So for example, we use crypto techniques like homomorphic encryption, multi-party computation, zero knowledge proof, so to achieve like privacy security for different applications of blockchain, like decentralized finance, digital identity for Web3, and so on. Right, so, and then actually my research cover both classical and post-quantum crypto techniques. So yeah, so later maybe we can also discuss like what's the difference, why actually it's very challenging to say build up like say a post-quantum blockchain system, and also how to apply post-quantum techniques in applications. Yeah. Okay.
Yeah, by the way, when Professor Yang said about the crypto, he's actually referring to cryptography.
Oh, right.
All right. Maybe I will do it, okay, and then Professor Wang will do it. So just like what Professor Yang said, I used to be the supervisor, the PhD supervisor for Professor Yang when Professor Yang was still a PhD student. He's one of my best students, and we wrote a lot of papers together. And at that time, we have been doing key exchange, key management. So key management has been a very important topic, which basically talks about two parties, they have never met each other, how they will be able to exchange a secure key so that they can establish a secure channel. So after that, I've been a professor for more than 10 years. And then I joined the Hong Kong Research Institute called ASRI before setting up my first company, CryptoBLK. And then right now I'm running this project, Abelian. So I've been feeling very blessed to have all the cryptographers supporting each other and then build this one. Maybe we can also talk about a little bit about the history of Abelian as well. Yeah. So maybe next, Professor Wang.
Okay, yeah, thank you. Yeah. So I'm Huaxiong Wang. I'm professor of School of Physical and Mathematical Science at Nanyang Technological University in Singapore. And I did my PhD in Israel. And after my PhD, I worked in University of Australia about 10 years. And then I moved to Singapore in 2006, and I worked there from there until now. My area have been working on quite a few different topics in cryptography. For example, secure multi-party computation, fully homomorphic encryption, post-quantum cryptography, and also AI blockchain as well. Yeah.
Yeah. By the way, Professor Wang got 2 PhDs. Yeah. So one in mathematics, and then maybe mathematics is not challenging enough, and then Professor Wang moved to focus on cryptography. So Professor Wang has been well known on multi-party computation, privacy retrieval technology, different kinds of threshold cryptography, like secret sharing as well. So for example, when we talk about multi-sig in blockchain, we are actually, I would say it's kind of like using the entry level cryptography when we do the multi-sig. So recently I've been very excited to see MPC have been using quite widely in blockchain as well. So maybe the first topic I would like to talk about is that actually this morning I talked about NIST, NIST, the National Institute of Standards and Technology. So basically back to 2016, the NIST, the American NIST, started doing the standardization of the post-quantum cryptography. I would like to hear more from the cryptographers over here, like with their involvement, why it's been taking so long, like since 2016 and this year, after like 8 years of work, we just got the first 3 standards or 4 standards come out, 4 schemes coming out as the first batch of standard for the post-quantum cryptography. And then right now we are actually making use of those post-quantum cryptography to build blockchain systems. So could you please share a little bit about your insight, like how it works, why it takes so long, can we be faster, and why that's so important for the industry, for the blockchain industry?
Yeah. All right. Okay. So I think for crypto, usually we need sufficient time to actually analyze whether the schemes are secure. For example, if you look at elliptic curve, so this elliptic curve cryptography was proposed, I think, in the 1980s, but then until like 2000, after 2000, we started to use elliptic curve crypto. So it took 20 years for cryptographers, mathematicians, to study whether there are any vulnerabilities within the system. So for post-quantum, actually, I think the time for NIST actually to evaluate whether this kind of systems is secure, actually it will take time. So even if you look at the candidates, so there are a few families of post-quantum crypto algorithms. Say we have the lattice-based, code-based, multivariant, hash-based, and then isogeny. So the isogeny-based scheme, originally there was one, like SIKE, but then later, after a few years, actually it was broken, totally broken. Then NIST need to drop this scheme, right? So, and then even for lattice, early this year, actually Professor Yi Lei Chen from Tsinghua published a paper. So actually, the paper, although later people people found actually that there was a bug in the paper, but actually it's very close to say to the point where actually lattice-based crypto could be potentially broken. So actually, when we try to establish a standard, whenever needs to want to establish a standard like SHA-3, AES, it always took a long time because we need to measure the security, measure the performance, so evaluate from all the perspectives. So actually, yeah, that's the reason I think it took such a long time to publish, say, just 4 algorithms for now. But there are, I think, a bunch of algorithms still under evaluation. Later will be included in the standard. So I think this also brings a question how do we enable crypto agility, right? So I think especially for blockchain, because if you want to upgrade the system to adopt a new, say, crypto algorithm, actually it would be much more complicated than a normal, say, information system, right? So I think early this year, actually, or last year, actually, Duncan, you wrote a yellow paper about this post-quantum PQ bridge. I think that actually could be a potential solution. So, for example, say, although NIST already standardized lattice-based scheme, but we don't know. Maybe in a few years, someone found even the classical computer can break lattice-based scheme. So then we need to quickly switch to another scheme. So in this case, maybe what you propose could be some approach. I think the idea from high level, actually, this is a very excellent and brilliant idea. So basically, you want to bridge, say, the normal ECDS-based blockchain with post-quantum blockchain, so that actually, I think what you wrote in that yellow paper is to use a post-quantum blockchain to protect the classical blockchain, but it could be the other way around. So if, say, the post-quantum blockchain actually later found insecure, then you may also use a classical one to say within 5 years, ECDS is still secure, then you may use that blockchain to protect the other one. So this could be extended to, say, a more general sense. So you can have some blockchain implementing code-based crypto, some using lattice, some using, say, multivariants. Then if, say, you can build a bridge, then they can protect each other. So if, say, one scheme is secure, then still, because the other blockchain, actually, you have some, say, checkpoint that can help ensure, actually, that vulnerable blockchain, the account will still be secure. So I think that could be maybe something we can further explore, whether, yeah, this can be a way to address, say, the crypto agility in blockchain domain. Yeah, okay.
Good point. Professor Wang, would you like to add something?
No, I just try to. Well, okay. So in terms of crypto, we have the cryptology. It means cryptology combines 2 directions. One is cryptography, is refer to design the scheme, the security scheme. Another one is cryptanalysis, try to attack the scheme, and they always hand by hand to develop together. So this is also the reason you just mentioned why this needs to spend so long trying to come up with this standard. They needed to a very few rounds of the design, attack, defend, and all this kind of procedure. I think this, yeah.
And I remember back to 2016, at the very beginning, there were more than 50 submissions there,
yeah.
For the post-quantum standardization?
It is 82 submissions and
82.
then 69 into the first round. Yeah.
Yeah, so 82 submissions, 69 got into the first round,
yeah.
And then after 3 rounds,
yeah.
And
yeah.
There were only less than 10 remaining.
Yeah, in the moment, unfortunately, selected 4 candidates, and most of them are based on lattice. Another one is based on Huaxiong. They have another 4 candidates that are going to another round, try to select 1 or 2 based on coding. Yeah, so this still takes some time. but we expect that by 2000 and the next year, the final decision will be made and let the final candidate will become.
Yeah. So what we can see is that actually in the last 8 years, like there were more than 80 submissions coming from all over the world, like different cryptography groups in the world, they submitted to the NIST. And then after spending 8 years, 5 were selected as the first batch of standard. And then maybe next year, we are expecting to have maybe a few more algorithms that will be standardized as the post-quantum, we call it the cryptographic primitives, right? So just a little bit more about that. There are 3 signature schemes, and 1, we call it the KEM, but basically they're kind of like encryption schemes, right? So 1 encryption scheme and 3 digital signature schemes. Are you going to expect more encryption schemes coming up, being standardized, maybe next year?
It's better for based on coding based. Code-based.
Yeah. So right now we have Kyber, Falcon, Delphium. They are all lattice-based.
Yeah.
And they are standardized. And then we have 1 hash-based as the signature scheme.
Correct.
So the industry is actually expecting to have some other methods for achieving post-quantum, and very likely code-based could be the next ones to be standardized. In fact, one of the parts that Guomin mentioned is that maybe in the future we may have more post-quantum blockchain systems, and then if we bridge them together, then it's actually going to have some kinds of synergy, because we just cannot put all the eggs into one basket, which means if everything is lattice-based, and then if lattice-based is, say, broken or somehow, then we still have code-based, we still have hash-based. So that's why last year I wrote that yellow paper, and maybe hopefully the research community will be able to come up with a solution to implement that yellow paper. That would be fantastic. That would be very helpful. So as we can see, the NIST is actually having a very prudent exercise in order to make sure those algorithms that we are using are really secure. My next question is more related about Abelian, is that I know we are using different kinds of cryptographic primitives to achieve different things, but our approach is a little bit different from the academic approach. The academic approach is usually like, I already have a algorithm, or I already have some kinds of technology, I want to build some product out. But for Abelian, it's quite different. Abelian is like, we want to achieve something. Here's a set of user requirements. Say, I want to be post-quantum, and also I want to have multiple layers of privacy. And what kind of cryptographic tools out there that can be used to achieve that? I would like to hear more from you about the privacy part, like what kind of technologies that we use to achieve the technology requirements that we have in mind.
Okay, so I think, so you look at this 140-page white paper for this Abelian. So one thing is very interesting. They use delirium, which is the final list or this list for candidate as the building block. Okay, and at that time, I think the Abelian, when it developed, the developers start to design this Abelian, it was some 2018 sometime. And that time, we don't know what is the final list for this needs competition. So I think this is a very good decision, maybe also some luck, I guess. So using this, I think the also approach is quite amazing also, because of what? We all know that quantum security is very important. You have Bitcoin, you have Ethereum, in all these different coins. So they try to different value approach. For example, by packing this existing blockchain into post-quantum solution by using some sort of engineering approach. But Abelian take another approach. They're starting from the basic, the fundamental point of priority. So use this one as a building block and learn to develop new functionality. So for example, if later on they needed to develop for this 3-layer or this privacy, they needed to use something like homology commutable scheme. Okay, but there's no such scheme based on lattice. So what people debate lattice-based commutative scheme. They needed to have this verifiable inclusion scheme in order to achieve this accountability. Okay. They also needed to use this zero-knowledge ranging proof. Because I have to prove to someone else I have this amount of money, for example, around 100 to 1,000 in my pocket, in my wallet. So later, when I spend, okay, so $110, you are happy to accept. Oh, no, $90. So this different parameters required by this additional requirement on this privacy. And all had to be published in the tier top conference and get approved from all the community to read, to check if all these proofs are correct. So I think this is a nice thing with this Abelian. Yeah.
Guomin, would you like to add something?
Okay, yeah, so I think the privacy enhancing technologies actually have been available like for quite a long time, right? So we have like a zero knowledge proof, we have like a commitment, and then for like I think for post-quantum or lattice-based designs, actually there are some major challenges, right? So I think one challenge is obvious, like most of people know, is about the size. Actually, the size of say, if you compare the ECDSA and the DLCM, right? So the ECDSA only need, say, maybe around 64 bytes, right? So, but then the DLCM will require about, say, 2 kilobytes, right? So that's already a huge difference. I think if you extend this to the more complicated, like crypto primitives, for example, ring signature, right? So like a homomorphic commitment, zero knowledge. Actually, the size will grow like a much bigger. So this is actually, I think, one drawback of a post-quantum crypto system, like most people know. But then actually another challenge, I would say, actually is for example, if you use a signature, use the DLCM, there is a process called rejection sampling, right? So you need to restart the signing algorithm. If, say, when you produce a signature, it does not satisfy certain requirement. But then if, say, you apply these to more complicated, like a ring signature zero knowledge proof, then not just one component you need to restart. So many components you need to restart. Like, say, if you have a few statements to prove, you need to generate, because ring signature essentially you need to simulate signatures for other people in the ring. Then you may also need to satisfy this requirement. Then you may need to restart once one of the components actually cannot satisfy. So then in this case, actually you may, because the probability will just accumulate, right? So then you may need to run 10 rounds, 20 rounds before actually you can find a satisfying signature. So that's actually, those are the challenges we need to deal with because of the difference in the mathematical structure between the, say, post-quantum schemes and the classical schemes. Yeah, so I think, Abelian already used some techniques to overcome some of those challenges, but I think there is still space to improve, but it relies on, I don't think there will be engineering approach to address this problem, but will be still from the research community's effort to address those problems.
Yeah, just like what I mentioned this morning, in order to achieve or resolve the trilemma of blockchain, decentralization, security, as well as scalability, our approach is to do it in 2 layers, which means we are not going to address the scalability on layer 1. So layer 1, we will just focus on security as well as decentralization. And then we build a bridge between layer 1 and layer 2 And then we run the smart contract as well as improve the scalability on layer 2, right? But I have to say we are pretty lucky, right? By picking the structure which is the lithium-based back to 7 years ago when the NIST standard just got started. Of course, it's not just luck, right? We love the structure. We love the mathematical structure of lattice-based cryptography. But actually, if I remember correctly, we also explore the possibility of using verifiable encryption, post-quantum verifiable encryption, or the homomorphic commitment scheme as well. And finally, we use the post-quantum lattice-based commitment scheme to do it. The next stage that I think we need to focus on might be related to smart contract, how to ensure the privacy. And I know Guomin is working something on that area. Will you be able to share a little bit before your paper is published or something on the private smart contract?
Okay. Yeah, I just started this like a research area, I think last year. So they actually compare with, say, for example, the other like privacy preserving techniques, like zero knowledge proof and commitment or signature, ring signature, and so on, group signature. So private smart contract actually received less attention, I would say. So in the literature, there are not many works in this direction. So, but actually, this is a very important area we must like address, because we know for smart contract, by default, actually, people can see all the state of the smart contract. So you can't actually protect the accounts which are managed by the smart contract. So in the literature, actually, there are some approach. So two main categories. One is based on trusted hardware, say trusted execution environments like Intel SGX. Now there is a new generation Intel TDX. So what they do is to put the smart contract. Basically, you have the state of the like a smart contract encrypted, but then the trusted hardware can do a decryption. So basically, the users will need to send the transaction to the like TE, the trusted hardware. Then the trusted hardware will load the state, decrypt the state, perform some computation, update the state, then write the updated state in encrypted form back to the blockchain. So this approach has a problem. So it is the main problem, in my view, is not compatible with the Ethereum like smart contract. So another approach actually is based on crypto. So they use homomorphic encryption. So in this case, actually, they let the smart contract operate as usual, but they can do computation on encrypted data. So homomorphic encryption is a natural solution for this purpose, because like we have a partially homomorphic and a fully homomorphic encryption. So fully homomorphic encryption, that means you can do arbitrary computation on the encrypted data. But because of the bootstrapping process, actually, it's not very scalable for large like computation yet. But then partially homomorphic encryption, if you just do like addition, then actually there are some efficient schemes. So currently, the private smart contract based on, say, the Palia or this L-gamma like encryption, actually they can do the smart contract computation on encrypted data. So then it becomes compatible with Ethereum like a blockchain, the smart contract. So I think in this area, what I want to do is how about we use both, right? So for example, you still use like homomorphic encryption to do some say computation, right? So on the other hand, so if say we want to satisfy the regulation requirement, the compliance with the regulation, then you may use some trusted hardware. So the trusted hardware, because we do remote attestation, people can guarantee say it will only like do the expected computation, not like revealing some sensitive data to even to the regulation body. So in this case, maybe the TE is not to execute the smart contract, but to ensure like the TE, the trusted hardware, can get some information that is required by the regulation body. But on the other hand, you can still run the smart contract on encrypted data in the normal way. So that's something I'm now exploring with my postdoc. Yeah, thank you.
Yeah, maybe we can apply that on Q-Day, our layer 2 as well, down the road. In fact, if you look into Abelian, Abelian has the post-quantum security, which is there already, right? We achieved that. If you look into the privacy, we already have that 3 layers of privacy, and we can even fine-tune the 3 layers of privacy to have different kinds of forms, like the fully private one, the pseudonymous one, even the accountable one, which means we have the viewing key. Or even about the viewing key, we can basically separate the viewing key into different styles so that we can actually release some more information because of the regulatory requirement and so on. My next question is that you talk about homomorphic encryption. We also briefly mentioned about zero knowledge proof, like ZK SNARK, right? ZK SNARK is the most popular one nowadays being used at the blockchain industry. Would those be the great tools or the post-quantum version of those? What kind of things that we can build further on our Abelian ecosystem down the road, maybe in the coming 5 years, or maybe 2 to 3 years, that given that we already have the foundation, we already have the multi-layer privacy, we already have that Q-Day, despite Q-Day is not real time yet, right?
Yeah. In terms of JK SNARK, I think this year crypto, there's a paper they come up with a new JK SNARK protocol with the verification is 10 to 4 power. This is 10 million faster than the signature generation, which means that there's a good chance that can make this JK SNARK to be practical. Yeah.
That's a very good point. So basically, we have a breakthrough on the ZK SNARK for the post-quantum. Is that also lattice-based?
Yeah, also lattice-based. Yeah.
Sweet. Yeah. So we have all lattice-based over here. But just one statement is that we are not like lattice-based only. All right. So as I mentioned, we are basically like use case driven. Like we want to achieve something, but we don't have the burden of lattice-based only. We use lattice-based because of its like elegant mathematical structure. But doesn't mean that in the future maybe we have a big news coming out that we have some hash-based primitives that we use on our Q-Day layer 2.
Just to add on the homomorphic encryption part, actually, if you look at the existing like a fully homomorphic encryption schemes, the state of that schemes are actually all lattice-based because the nice feature, like a homomorphic feature. So actually, a lattice-based scheme has some inherent like a homomorphic feature. So that's why the existing like FHE, fully homomorphic encryption schemes, actually they are all lattice-based. So yeah, just to add on the also like when I talk about the trusted execution environment, they still use public key crypto. So eventually, if we want to use them in the post-quantum application, we will still need to like upgrade the trusted hardware to also support post-quantum crypto. Yeah.
Got it. So the final statement I would like to make is related to trusted computing that you mentioned about. I know some of the other projects are using trusted computing. I'm just having some kinds of reservation of using trusted computing when I talk about the decentralization and how much that you can reach out. What's your view regarding like making use of trusted computing in the blockchain industry?
Okay, so I think some people criticize this trusted hardware because there are issues like side channel attacks and so on. But actually, what we want to do, for example, in research, of course, I think maybe from industry perspective, maybe practicality, efficiency is more important. But then from research perspective, sometimes we want to reduce assumption on like trusted hardware on one hand. Maybe Intel, AMD, they can continuously improve their approach, their design to resist those attacks against trusted hardware. On the other hand, actually, what we do is to combine crypto with like a trusted hardware, because I think crypto in general, if you want to use crypto to do management, like operations, that's very expensive. Then we can use trusted hardware to do management tasks, but underlying operations we still rely on crypto. Then we can reduce the trust. For example, we don't require confidentiality requirement, but just the integrity. We only need to ensure the trusted hardware will run the program honestly. We don't need to protect the internal state. Even if a side channel, it doesn't matter because we will use crypto to ensure the confidentiality. So in that way, I think we can maybe address some potential concerns about trusted hardware. Yeah, that's my perspective. Yeah.
All right, makes sense. Sorry that we are running out of time. I still have a lot of things I want to share, but both professors will be here for the rest of the day. So if you have any questions related to cryptography and also the future development of Abelian, feel free to come and talk to us. We will also take the opportunity to discuss more about what's next and what kind of other cool technologies and cool stuff that we can build on Q-Day layer 2. So thank you very much. Thanks for having us.
Thank you.
Thank you.